All right. Okay. Today we will talk about the content of chapter 24 on the MR angiography and the flow quantification. So this will be the last chapter of this course. Okay. So for previous classes, the contents we are going to need for this today's content will be for the flow and flow compensation concepts that we just discussed last Tuesday, 2 days ago on chapter 23. And also we also need to revisit the steady state signal in chapter 18. And today's content, the first one I'll introduce some of those widely used MR angiography techniques, and then we'll discuss the phase contrast flow quantification, or what we call the PCFQ techniques. All right, so first let's take a summary review of the MR angiography. So MR angiography is the technique that is used to visualize specifically the arteries. That's the name angiography. So MR angiography is used to image the arteries in the human body, including in the brain, in the neck, in the liver, in the kidney, or in the legs. So any techniques that is used to give you the information about the arteries in your body is called MR angiography. So there are many different acquired field techniques that can be used to do angiography in MRI. So we can divide them roughly into several categories. The first category is the bright blood methods. So the bright blood methods means that the arteries will appear bright with high signal in the MRI images. So this kind of method will include a so-called time-of-flight TOF method, contrast-enhanced MRA, or CE-MRA, which uses gadolinium-based contrast agents to reduce the T1 of the blood. And also, as we have seen before, the steady-state free precession SSFP will give you a T2 over T1 weighted, and that would also make the blood appear bright in the SSFP images. There are also another type of MR angiography methods. They're called the dark blood methods, or the black blood methods. So this kind of dark blood method includes the double inversion recovery. We'll take a look at it later. Flow dephasing, saturation, the use of saturation band to saturate the inflowing blood. Susceptibility weighted imaging, but which is mostly used for imaging the veins, but I'm also showing here to give you an idea of the dark blood image method. And also, double method can also be using the contrast-enhanced method, but in this case, we will be using the iron-based ultra-small particle of iron oxides. So this one will give you significantly increase the susceptibility of the blood. So when the susceptibility of the blood itself increases, it will significantly shorten the local T2 star of the blood. So that means the blood signal will decay very fast, and you will get a very low signal using any T2 star or T2 weighted images. And also there is a quantitative method for MR angiography that we will be talking about later, which is the phase contrast flow quantification. And based on the phase contrast flow quantification, there is some lately development of the 4D flow quantification to visualize the flow in the heart in a heartbeat positivity cycle. We will see an example of this later. Okay, so first let's take a look at time of flight technique. So time of flight, the flight here means the moving speed of the blood. So let's consider that this is the vessel, and if we are, doing excitation of a slice. So this is a slice that we excite, which is perpendicular to the vessel. So the flow, the blood flow just move in a perpendicular direction to the slice. So when we do the excitation, and let's assume the RF pulse has the effect of RF pulse tipping is instantaneous. So that means when we do the excitation, we will excite the spin, right? That is defined inside this slice profile. So we'll excite the blood that has just passed this passing the slice, and then after a while, and then after the excitation, we can see that signal of the static tissues, they will decay, right? As the FID in terms of T2 star. So it will decay, but it still have the signal. But then the blood itself will move forward. So then after a while, the blood that is has come to this specific location is the blood that was outside of this excitation band. So that means the blood at this moment they have not seen an RF pulse, so they are not excited. Okay, so this is the what we call the inflow effect or outflow effect. So the inflow effect means that there is unexcited or the unsaturated blood that move into the imaging slice or the imaging slab, if that's the 3D case. Or we can also call this the outflow effect. The outflow effect is that flow out of those excited blood spins of the imaging slice or the imaging slab. So that depends on which one you are interested in. So we can see later that depending on the application, this same phenomenon we can call this same phenomenon either by the name of inflow or by the name of outflow. So there is a critical speed when we were talking about this. If we are talking, if we are exciting a slice with a certain thickness, and the critical speed of the blood for the blood to for a total inflow effect or a total outflow effect is this just simply determined by the slice thickness over the TR. So that means if the blood flow is higher than this critical speed, that means that for the next excitation, the next excitation will seize the blood that has not been excited before. If the blood flow is lower than this velocity, then part of this excited blood will remain in the original slice, and it will experience another excitation RF pulse. So this is the critical speed we are looking at to discuss the time of flight effect. Okay, so how does time of flight effect? As we saw before, time of flight is bright blood method. So how can it give us a higher signal? As we see before, the steady state incoherent, as in spoiled as in a signal spoiled gradient echo sequence, we can see that for the long T1 tissue, like the blood, it will have a lower you have a lower steady state signal than the other tissues, right? So that means if we collect the data in a steady state, we'll be observing a lower blood signal, right? But this is but when we are talking about the buildup of the SSI signal from the equilibrium state, so when we first apply the few excitation pulse instead of many excitation pulse, we can observe that the signal actually there is a signal decay, and if we look at this portion, just with a limited number of RF excitation, before everything reaches the steady state, we can see that the blood at this point actually has a higher signal than the white matter or gray matter, regardless of its long T1. This is because the blood itself has higher spin density, right? So for a higher spin density, it will give you a higher initial signal, even though at the steady state signal it will give you a lower steady state signal due to its long T1. So the idea is that if we collect the data at this point, we will be observing a higher blood signal than the tissues. If we collect the signal at this point, right, at the steady state, we will be observing a lower blood signal than the tissues. So the idea of Timeofflight is that we obtained a high blood signal or the unsaturated blood signal, while we obtained the tissue signal at its steady state, which is lower. Okay, so let's just bloom up the exaggerate it a little bit. So let's say this is the total thickness of the slice we are collecting, and we are talking about a 2D slice, right? So when we do, and this is the vessel, and surrounding it are the tissues. So when we do the give the first excitation pulse, it first excites all the blood inside this slice profile, inside the slice thickness, right? So then before the second RF pulse is applied, the time is TR, because the blood flow is flowing, so that when we are applying the second RF pulse, part of this newly inflow blood will only sees the second RF pulse as its own first RF pulse, while the rest of the blood that is still remaining in the profile of the slice, they are seeing this as the second RF pulse. So if this goes on and we apply RF pulse, then we can see that for different for the blood spins that has moved into different depth of this slice, it will experience different numbers of the RF pulses. So we can see that for different section of this blood, it will have different different signal intensities, as we are seeing here, right? So this would be the newly, and here this will be the newly inflow blood, and then it will be the, and then as the blood flow flows into the slice, it will have a decreased signal. So if this we are talking about a 2D excitation, so this is the 2D slice. That means the signal we obtained for this slice, for the blood in this slice, actually will be the sum of all these different blood spins. So this will be shown as this is a sum of all these different sections of the signals. Okay, so that means that for this one, it will have a very high signal because it's far from saturation. And for this one, if it has experienced a certain number of RF pulses, now it will become more saturated and has a lower signal. So in this case, if using a very thin 2D slice, that means we will be only having a small number of these segments for a certain number of RF pulses or a certain number of TRs. So that means the blood inside these veins, the blood inside this slice, they're mostly unsaturated. They are all those inflow of fresh blood. So that means we can obtain very high signals for those vessels. But for the tissues outside, it will be always seeing the it will be always seeing the n number, number of n RF pulses. So that means the tissues outside the vessels, because they are static, they are all saturated. So that means they will have a very low signal. So using this inflow effect, we will be obtaining a very high signal in the blood, while we are having a very low signal in the tissues. So that means the tissue we collect may have the signal at this level, as it has experienced a lot of RF pulses. But for the blood inside the slice, we may be their signal intensity is located in this range. So that means we obtained a very high signal here. So so this one because this is actually a combination of blood spins that are T1 saturated to a different extent. So it is no longer its original. The signal is no longer determined by its original T1. So we can define an extra T1 term that is related to flow, as shown as determined by this slice thickness over its velocity. So the effective T1 here now would be would be determined by this relation. So that means if we have a faster flow here, we'll have a smaller T1 term that is related to the flow. And for a smaller value here, we'll be obtaining a smaller value here. For smaller value of smaller T1 flow, we will be having a larger term in here, as it's inverted value, and then that means the T1 effective will also become smaller. So with an effective smaller T1, that means we can be able to obtain a higher steady state, so-called steady state, but it's not a steady state as we introduced before. So this is the 2D case. So in the 2D case, the blood signal is a sum of different blood spins that has experienced different RF pulses. So it's the sum. But for the same plot, actually we can take a look at the inflow saturation effect in a 3D. So for 3D, this is let's assume this is the imaging slab, and we will be doing the partition encoding along this direction, right? So with this partition encoding, actually we will be collecting, be dividing this thickness into different voxels, and for different voxels, we'll be able to collect the signal intensity at different section of this inflow effect. So that means we can directly reveal this gradual blood saturation as the blood goes into the imaging slab. So here is the example here. So this is the I think this is the contrast enhanced one. So this is the vessels that we should expect. But if we are simply using the total slice thickness, right, a very thick imaging slab along this direction, and as the blood flows in from below, which is the arteries from the heart up to the brain, and for the veins flowing down to the heart, from the head to the heart. So we can see that as the flow goes deeper into the imaging slab, we can clearly see the blood becoming more saturated. Right. Now it has become has a lower signal than the tissue. So now it cannot be seen at the end of the as it goes very deep into the slab. So also we can see that arteries have a higher flow velocity than the veins, because let's assume that the blood experience a certain number of hour pulses before it disappears due to its saturation effect. Then we can see that the artery blood can flow much further into the slab than the veins, right? Because so we can see that the arterial blood flow has a higher velocity than the veins. So that means if we for 3D imaging and to do the time of flight, we cannot use a very thick slab, 3D imaging slab, because at the end of this, or the other side of this slab, chances are we may not be able to see those vessels. Okay, so yeah, as we said before, the time of flight, the TOF MRA has a low tissue signal, which is at steady state. But it will have a high inflow blood signal before those blood reaches its own steady state. So the blood is not saturated, so that we can have a higher blood signal than its surrounding tissues. So that's the working mechanism of the time of flight MRA. And when we are doing the time of flight MRA, we need to have some considerations on the sequence and imaging parameters. So, the sequence itself usually is a flash sequence or a gradient echo sequence, right? Because gradient echo sequence can give you steady state incoherent signal, which is directly T1 weighted. So for T1 weighted, we can achieve this saturated tissue and unsaturated blood. So we need to consider the flow compensation. As we saw before, if we do not do flow compensation, the flow itself will lead to a dephasing of the signal, and will lead to reduction in the blood signal. So if we do not do the flow compensation, the blood signal will decay even much faster. So we may not be able to see the vessels being higher than the tissues. And the best way is that we have the perpendicular inflow effect. So that means the slab we are selecting, the imaging slab or imaging slice. It would be best if we have this the vessels inflow perpendicular to that imaging slab. So imagine that for another extreme case, if we have these vessels flowing in plane inside that imaging slice or imaging plane, that means those blood will see as many RF pulses as the steady tissues. So that means the blood will be heavily saturated. So another idea to improve the TOF effect for 3D is that we can use multiple thin slabs or multiple thin slices for 3D and 2D respectively. So let's go back here. Right. So if we use a slab of this thick and the blood flows in from the bottom, we cannot see it. We cannot see it. The blood in here because it's become saturated. But if we just reduce the imaging slab to this part, right, that means for this whole imaging slab, we'll be able to see a high blood signal. And then we shift this imaging slab and do the imaging, collect the another 3D slab here. We will also be seeing a much higher signal for this for the blood inflow in here. So the strategy is that we collect multiple thinner slab, and then we can get a better TOF effect, and we can be able to show the vessels more clearly, just like this. And also, when we're doing TOF, we do not want to have too much, signal decays. So it would be great that it would be use a shorter TE. We can use a shorter TR, but that will have to depend on the flip angle. Usually the flip angle should not be too large. If we use a flip angle too large a flip angle, that means that it will drive the blood to steady state much faster, right? But if we use too small a flip angle, then the background tissue, the gray matter or white matter, they may not be, they may not have low enough steady state signal, so that the contrast between the arterial blood and the tissues may not be that great. So there is, must be a compromise between the TR and flip angle that we use. Another idea is to use so-called tone pulse. The tone pulse is used for 3D slab excitation. So the tone pulse does one thing. It is a spatially varying flip angle along the slab thickness. So the tone pulse is very interesting. So let's say this is the slab. So this is the slab with a thickness, right? So and we have a vessel going through it. So normally, if you simply use a sync pulse, right? So the excitation profile will be something like this. So we can consider this is the effective flip angle profile. The flip angle profile here. So that means when the blood flows in here, it will seize the same flip angle as it will seize the same flip angle as it goes in. But for the tone pulse, it will have a spatially varying flip angle. It will be something like this. So that means that when the blood first flow into the slab, it will seize a higher flip angle. And as the blood flows further into the slab, it will seize a smaller flip angle. That means the blood will reach a steady state, in a slower, pace. So that means when the blood reaches a certain depth of the slab, it will be less saturated than using a normal sync RF pulse. So most of the time when you use the TOF MRA on the modern scanners, usually it will be applying a tone pulse instead of a sync pulse. All right. So as we mentioned before, we can do the TOF MRA in both 2D and 3D. So this is the illustration of doing 2D or 3D. For 2D, we use multiple slices that is perpendicular to the vessel, while the 3D we use a single imaging slab, perpendicular to the TOF. Perpendicular to the vessels. So when comparing them, we need to consider a few things. So first is the SNR, the signal to noise of the image, and for 3D, we definitely can get a much higher SNR than the 2D case because we have multiple partition encoding steps that will reduce the noise level. And also the resolution of the 3D along this slice select direction will be much higher. We can actually set this resolution to arbitrary for the 3D case. But for the 2D case, the slice it is limited by the slice thickness, and due to the RF pulse and the SNR restriction, we cannot use a very thin imaging slice for the 2D case. So that means the 2D resolution along this along the slice select direction will be limited. And also the second thing we need to consider is the blood saturation effect, or the contrast to noise ratio of the blood between the blood and the tissues. So as we saw before, the 3D has the problem of saturation of blood further into the slab. While in 2D, most of the time for those main vessels, it will have no problem revealing a very strong TOF effect. But on the other hand, we need to, as for this resolution, we can see that the vessel contours, it will be much smoother in 3D because the high resolution along the slice select. And also for the 2D, there is also one problem. If the blood is flowing too fast, it's faster than the critical velocity we saw before. And then if we concatenate all those slices together and do a coronal view, we will be seeing all these discontinuities in the blood, in the vessels. This is just simply because the blood is flowing outside, flowing too fast, and there will be some signal voids created by the outflow effect. And also the imaging time is a very very important for 3D. Most of the time it requires much longer imaging time than the 2D case. And also we have to depend on what kind of application we will be using. Most of the time, if we are collecting the MRA in the neck, it will be enough to just to use the 2D TOF, because the blood, the vessels in the neck, they are all very thick and the blood flow are very fast. But for imaging the arteries inside the brain, so usually the 3D version of the TOF will be more popular, because we need to obtain a higher resolution and a higher SNR to reveal those much finer details of the vessels inside the brain. Multi-slice and slab imaging, as we have discussed before. And also one thing we need to keep in mind is that TOF effect actually applies to both arteries and veins, right? As both arteries and veins, they have flowing blood, and the flowing blood may become maybe a little bit less saturated. So as we see before here, we can obviously see the two sets of arteries, two sets of vessels. This is the artery and this is the vein. We can tell this because we know its flowing directions. But if we collect a really good, tough MRA result, we just by the intensity of itself, sometimes we may not be able to tell which one is artery or which one is veins. It's easier to tell in the neck because the vessels in the neck is the anatomy of the neck is relatively simple. But sometimes in the brain, it's a little bit difficult to tell if both the veins and arteries have very similar signal intensities. So we need to keep this in mind. Okay, so time-of-flight MRA is a technique, a bright blood technique that is dependent on the flow of the blood. But on the other hand, if we apply the Earth's contrast agent that can reduce the T1 of the blood, that it can become a flow-independent method to image the vessels. So let's review the SSI signal. The steady state incoherent signal is in this equation. You all know that from doing it in the exam. So we can see that if we increase this T1 E1 term, if we decreased the T1 of the tissues, and we can actually obtain a higher, possibly higher signal for a certain flip angle. So to increase the SSI signal, and from a theoretically point of view, we can use a shorter TE, so that there will be less T2 or T2 star decay. We can use a longer TR so that we can reduce its term. We can use the Ernst angle for the blood, and then we can also use the Ernst angle to achieve the maximum signal for a given TR. And we can also reduce the T1 or increase the T2 of the tissues, so theoretically speaking. But normally, it's a little bit difficult to increase the T2 of the blood. So it's easier to reduce the T1 by injection of the contrast agent. So for the contrast-enhanced MRA, it uses this method to reduce this strategy to increase the SSI signal for the blood. Okay. Yep. As we see before, the contrast agent is a gadolinium-based chelate, or usually we just use GD to represent it. There are several products, but all of them are very good at reducing the T1 of the blood. So when the blood, now if we have significantly reduced the T1 of the blood, and it's now shorter, even shorter than the tissues, than the T1 of the tissues, then we do not need to use any tough inflow effect, because at steady state, the blood signal would be much higher, because it has a shorter T1, and it also has a higher proton density. So for contrast-enhanced MRA, we can use a fixed lab, and it is not flow dependent. So there's no need for TOF effect. But of course, the TOF effect will be much enhanced if you look at the blood that has just flowed into the imaging slab. It will have a much higher signal. So for contrast-enhanced MRA, there are also several considerations. Just here 2 examples. This is the TOF MRA. We can see that it shows the major arteries clearly, but when the vessels become smaller, it will have difficulty to show because of the first thing is the inflow saturation of the blood. When the blood flows into the smaller branches, it will has also experience more pulses to become more saturated, and also the blood flow would be slower in a smaller when the vessel becomes smaller. But for this is the contrast enhanced MRA. We can see that it can now further shows more details of the smaller branches of the arteries here. Okay, so for the consideration for the contrast enhanced MRA, first thing is of course the safety, because the gadolinium based chelates those gadolinium based contrast agent, they will be extracted out of from the bloodstream by the kidney. So if the patient has some kind of kidney problems, it is not advised to use the contrast agent to do the MRA. And then we can, with the much shorter T1 in the blood, we can now use even a shorter TR and a higher flip angle to further. On one hand, it can to enhance the increase the blood signal, and on the other hand, it can also further suppress the tissue signal. So we can see from the MIP, maximum intensity projected images here, this top image, we can still see a gray background that's from the tissues, while from this contrast enhanced, we can see that with shorter TR and higher flip angle, the background tissue is further decreased and suppressed or saturated. Then and in this way, it can also help to improve the contrast between the vessels and the tissues. And also due to a shorter TR, contrast enhanced MRA can be even faster than TOF MRA, and can give you even higher resolution in that sense. And since it's not flow dependent, no TOF effect is needed, the contrast enhanced MRA do not need to use tone pulse. But of course, similar to TOF MRA, we also need to consider the venous signals, because when the contrast agent goes into your blood, it's everywhere in your blood. So it will also shorten the T1 of the venous blood. Then it is also possible to show the veins in the final vessel map. So it is there will be some type of venous contamination in the final map. So we need to be aware of that. Okay, so the TOF and contrast enhanced MRA are two most widely used MRA, bright blood MRA method that is being applied every day. So there are also the so-called black blood MRA methods. So there are also many different versions of black blood MRA. So this one is one of them. Also, I was saying it is the most widely used black blood MRA method. It uses double inversion recovery RF pulse to suppress the blood. It also features in the TOF effect. So the idea is that first we applied a non-selective immersion recovery pulse. So for this non-selective immersion recovery pulse, it inverts everything, right? It inverts everything to the negative Z axis. Now immediately we apply a slice selective inversion recovery pulse. So this, the function of this is to selectively, revert those inverted pulse back to the back to its equilibrium position. So for this slice, they would appear as if nothing has happened. They would appear as if they are still at its equilibrium state, while all other regions, they still are being inverted. Okay, so if we remember that after the inversion recovery pulse, and the signal, the magnetization will slowly recover towards the equilibrium, and at one point it will reach the zero the zero magnetization along the z-axis. So that's how we do signal nulling using the inversion recovery. So this is the same then. After this double inversion recovery, we then wait a certain time, a certain TI, so that this TI is set to null the blood signal. Okay, so after the TI, the blood signal now has reached its zero longitudinal magnetization time point. And at this point, if we do another excitation RF pulse for this same slice, then for this slice, for the static tissue, because it now it has been flipped back to the equilibrium state, so it will be excited as if this is the first excitation pulse it sees. So there will be a normal signal intensity for the tissues. But for the blood, because there is no longitudinal magnetization at this time point, so it will not create any signal by this excitation pulse. So that means this the signal, the blood now has zero signal. So this would achieve a high tissue signal, while the zero blood signal. So this is the blood itself is actually being nulled at this point. Actually, I'm sorry. This is not based on the TOF effect, because when you do this non-selective excitation pulse, it flips everything. It flips all the blood in the whole sample, in the whole head or in the whole body to the negative z-axis. So that means this RF pulse, this inversion RF pulse, works for all the blood signal. So that means it's not TOF. It is not affected by the TOF effect. Okay, so another simple idea of suppressing the inflow signal using the saturation band. So this one is TOF, has the TOF effect. So when we so if we do excitation slab or 2D excitation slice here, and we have the blood flowing, for example, for the artery flowing from the heart to the head, and the veins from the head to the heart. So if we before we do the excitation, if we do a saturation pulse here, just above this excitation slab. So a saturation pulse is is a 90 degree followed by a strong spoiler gradient. So that means you first excite all the signal and then destroy it, and then you immediately after that, you do not have any signal to excite, right? So for this part of the blood, it will be saturated, and then we do and then we wait a little bit and for this saturated blood to flow into this imaging slab, and then we do the 3D excitation and as normally we do. Then there will not be any signal left to be able to collect it for this wing. So here is usually the setup. This is the yellow box shows the imaging slab, the 3D imaging slab, and we have put a saturation band above it, so that we can saturate all the other Venus signal. So for the so this is one example. If we do not put this saturation band, we will be seeing this just jugular veins in here. But if we do the saturation band, we will saturate the vein signal, and we do not see it in the final image. So if we similarly, if we want to see the veins, then we can put this saturation band below here to saturate this inflow artery blood. So this is another type of selective black blood MRA. The one before we see is non-selective black blood. Okay, so here is another very interesting black blood MRA, just simply using our spin echo sequence. So, for example, as we talk about, this is the TOF. This is the TOF effect. If we're using the bright blood TOF effect using a gradient echo sequence, right? So every time when we do the excitation, we will be exciting the new unsaturated blood, which will give us very high signals. So this is the TOF MRA. But if we use a spin echo MRA to do the MRA, first the spin echo is composed of two RF pulses. The first is the 90-degree excitation pulse. The second one is the 180-degree refocusing RF pulse. So when we know that if we do the 2D imaging with the spin echo, both RF pulse must be slice selective, and they all must be selecting the same slice. Okay, so this would be true for the static tissue because it's still at the same precision. But for the flow, for the blood flow, the 90-degree RF pulse would excite this part of the blood. But when it comes to the refocusing RF pulse, this excited blood will already have left this imaging plane. Instead, the 180-degree RF pulse works on the blood that has not seen the excitation pulse. So it works on the. So it would look like an inversion RF pulse to this new blood. So that means there will not be any transverse signal or excited signal for this part. So that means the blood signal is excited but not inverted. And when it comes to the TE, when the signal is being collected, this signal would have dephased due to first the flow dephasing effect, and also due to the T2 or T2 star decay. So this is the black blood using a spin echo image. So when we compare into this bright blood, we can see that all the blood signaled has become black, So this is a very interesting, because they are just both a simple gradient echo and a simple spin echo. And also, as we seen before, the steady state free precession MRA can also give you a bright blood MRA, because the SSFP signal, they are T2 over T1 weighted, and the blood signal, then the blood has our highest T2 over T1 ratio, so it will also appear bright in the image as we see here. So because of the very fast acquisition speed of SSFP, it is usually used to collect the dynamic imaging, flow imaging of the heart. Okay, so up to now, all those MRA techniques we talk about, they are all qualitative. So they can give you a image of the blood itself, but it does not give you any quantitative information about the blood flow. So the next one, we will use the phase contrast to discuss to see the how we can quantify the blood flow velocity. So to do the phase contrast, as we see before, if we just simply apply, okay, so to do the phase contrast, actually we need to, if we remember from last section that we talked about the flow compensation, if there is a gradient along the flowing direction, the flow itself will develop an additional phase, right? So we then to obtain the phase information that is related to the flow velocity, we can simply apply a bipolar pulse gradient, to obtain the phase information that is directly linearly correlated to the blood flow velocity. So the idea is the same as we saw before, right? The phase developed is the integration of the gradient and the velocity and the time. So the result, by solving this problem and for the bipolar pulse scenario, we can get that the phase induced by a constant velocity will be simply this gamma g multiplied by the velocity and square of the time, square of this duration of the gradient. Okay, so this bipolar pulse, we usually also refer it to the velocity encoding gradient, so which is also called Wank. So when we say the Wank gradient, we are referring to a bipolar gradient. And also, for simplicity, we also use a certain Wank value. So when we say a Wank value, it is determined by this relation, is the pi over the gamma g tau square. So it is coming from this equation, because if we want to obtain a linear relation of between the phase and velocity, and we know that when MRI scanners is storing the phase information, it only stores the phase information between a 2 pi interval. Any development of the phase outside this will be wrapped around and cause aliasing in the phase. So we don't want to do that. So we want to control control that the phase caused by the flowing velocity, they are within this 2 pi range. So that means we will allow this theta v to be maximally to be pi and minimally to be minus pi. So that means we use a certain Wank value. If we set a certain Wank value for the velocity, right, for the certain velocity, and then we can estimate how long. We can estimate strength and the duration of the bipolar gradient we should use. So there is 2 questions. Why we use bipolar gradient? Because simply from this equation, we can see that the gradient, as long as there's one gradient, we can observe a phase, right, a linear phase that is proportional to the velocity. So why do we need to use a bipolar gradient? Well, because it's so simple. If we do not use a bipolar gradient, then the 0th moment of the gradient will not be 0, and it will lead to a D-phase. So we need to use a bipolar to make sure that we can subsequently obtain a gradient echo or achieve a 0th gradient moment. And we can also notice that after this bipolar gradient, to obtain the phase and additional phase information related to the flow. For the readout here, we are also using the 1-to-1 flow compensation. So if we are trying to get additional phase information with this bipolar pulse, why do we need another flow compensation after this flow encoding? All right. So this can be one question for you to think about. Okay, so from this we can see that the phase of the image we can see that it is directly linearly proportional to the velocity itself, right? And for the gradient amplitude and the gradient duration, we can know about that because we set that. So ideally, the phase we obtained will be simply a linear function of the velocity. But there are several source of errors that we need to take into consideration when we are trying to extract the velocity information from the phase image we get. So the first source of the error will be the field inhomogeneity. If there is a background gradient, right? If there is a background gradient, then additional phase will be developed. Additional phase would develop, right, on top of that flow, on top of our applied bipolar gradients. So that means it will also lead to phase variation. Also, there can be some RF penetration effects, which is B1 field inhomogeneity. It can also affect the phase of the images. And also, as we seen before, there will be a known phase baseline. So because we do not know which can originate from different sources, maybe from the different coil elements, from distance from the object to the coil, the amplifier, something. So the phase, the baseline. So the phase we get actually would have another unknown baseline term here. If we do not know them, it's a little bit it's difficult for us to correctly estimate the velocity. And also, as we said before, to avoid phase aliasing, we need to avoid phase being exceed the 2 pi limit. So if we are using a low Wank value, and we are using we have the fast flow, and we will be observing a significant phase aliasing inside the vessels, and those phase will not be directly proportional to this. And also, but on the other hand, if we use a high Wank value and we use a slow flow, we have slow flow, then we'll have a very little phase development due to the flow. So that would lead to a low phase contrast to noise ratio, and it will be, and then the noise term would become very large, relatively very large for this phase velocity-induced phase. So that will also lead to an error in calculating the flow velocities. So there are a couple solutions. The first thing is that we can do acquire the phase image with two opposite Wank values, and then we do the subtraction or do a complex division between these two data sets. So in this way, we can remove the effect from this field inhomogeneity, the background gradient, or this unknown phase baselines, which is mostly used, mostly the major error source to estimate, to quantify the flow based on the phase values. And also, we need to set the Wank value to this pi over gamma g tau square to avoid phase aliasing. So most of the time we have a rough idea of the flow velocity in different body parts. So when we are doing the phase contrast on different body parts, we usually would set the Wank value to the maximum flow velocity of the known flow velocity of those body parts to get a good signal phase contrast maps. Okay, so with phase contrast, we can obtain the velocity of the blood flow, but most of the time in the that's one kind of flow quantification, is the velocity quantification. But on the other hand, it is also very important to understand how much flow, how much blood is actually going through the vessels within a given period. Usually it's during, for example, during the cardiac cycle. So how much blood is being passing through vessels. So the definition of the flow can be considered as the integration of the velocity and area of the vessels itself. So, but practically, we also it is more practical or useful to estimate the blood volume that passes through the vessel within a given duration. So usually, when we are doing this for a cardiac cycle, we will also have to use the cardiac gating to obtain the instant blood flow velocity at different cardiac phase. So this is with the cardiac gating, we can obtain that kind of information. So this is the example of the flow quantification that we do in our lab. So this is one of the very quick vessel map using the 2D Timeofflight. So it can give you a very nice map of those major vessels. And then we can use it as a localizer to set imaging plane for their phase contrast imaging. And when we do this phase contrast imaging with the cardiac gating, we can collect the blood flow at different time points of the cardiac cycle. So here here is the magnitude image of those major vessels, and here is the phase image of those vessels at different cardiac cycles, at different time point of the cardiac cycles. So we can see that for the arteries and the veins, because they have different opposite flow directions. So we can see that their flow, their phase is of opposite signs. And at different cardiac cycle time points, the blood flow can be fast and can be slow. So with a fast blood flow, we can see a higher, a higher value of the phase. But with slower blood flow, like at the diastole, we can see a much lower phase value in here. So here is the example of this blood flow. So when we draw a region inside these vessels and extract this phase, and then just use that relationship between the phase and the velocity, we can come up with all these maps with the average flow, the integrated flow, which is how much blood volume has passed through that vessel along the whole cardiac cycle. And this is the volume flow rate. So that means at any certain given time, how fast is the blood flow is going through the profile of the transition profile of the vessels. So in here we can see that for the arteries and for the veins, they have basically have an opposite flow phase. Actually have opposite phase and flow direction. And then we can also see that there is a major reflux in the right internal jugular vein. So that means it's not a very good a good thing to have. Okay, so here are some examples. So here is one of the flow dephasing imagings. So it's one of the black blood images. So you can see that it uses a very low Wank value. So with a very low Wank value, all the blood, most of the vessels will have a significant phase aliasing and significant phase dephasing effect. So that means the signal will cancel each other very quickly for the blood. So it will lead to a very low signals in the blood. So here is we can see that all the vessels they are black, and in here we can see we are seeing a lot of vessels, and they include both the arteries and veins. But for the next one, it's just a normal TOF, 3D TOF with flow compensation. Then we can see that we will be mainly seeing the arteries in here because of this significant inflow effect. And also with the flow encoding, which is based on the phase contrast method, but it does the phase contrast along different directions to calculate the flow in a 3D dimension. So it gives you the flow information for arbitrary directions. So this is the 4D flow method developed by Michael Macro, and they have been able to show all those blood flow and the flow vortex within the heart So this is a very the latest development of the flow quantification methods. Okay. All right. So the homework is these 5 questions, and so for next section we will do a brief review, and we'll discuss about the 2 exams, the questions, and okay. All right. Thank you.